You know, you really can't open a news feed these days without seeing something about artificial intelligence. It's everywhere.
Absolutely everywhere.
But behind all those headlines about like groundbreaking models and, futuristic applications, there's this really complex infrastructure making it all happen. And
Yeah.
if you're trying to wrap your head around the nuts and bolts, maybe even thinking about something like the NCA-AIIO exam, it can feel like learning a whole new language. Seriously.
It absolutely can. I
Yeah.
mean, the world of AI infrastructure and operations, it's just constantly evolving. There are new technologies, new approaches, like all the time.
Yeah.
So for someone just trying to get a handle on the essentials, yeah, it can definitely feel overwhelming.
Well, that's exactly why we're doing this today. We've kind of sifted through a stack of info, including some stuff related to that NCA-AIIO exam.
Right.
And our mission really is to pull out the critical insights for you. Think of this as like your shortcut to understanding what really matters for the infrastructure powering AI.
The common roadblocks, the strategies that actually work.
Exactly. The common roadblocks and, yeah, the smartest ways to navigate them.
Precisely. And, our aim isn't just about helping someone prep for a specific test. It's really about providing practical, real-world knowledge.
How things actually work.
Yeah, how these AI systems are managed, how they're optimized day to day. So we'll be digging into some typical challenges and the most effective solutions, drawing right from those exam-style questions and the logic behind them.
Okay, let's dive right in then. So one of the most fundamental things, right, when you're pushing these really high-powered AI models is dealing with a very real, very physical challenge. Just keeping the hardware cool.
Yes, heat.
Yeah, our first point comes from a situation where, like, NVIDIA GPUs are getting so hot during intense training that performance actually drops. That's the thermal throttling, right?
It is. And what's fascinating here is that, even with all the super sophisticated software and algorithms, we're still bumping up against basic physics, heat generation.
Right.
GPUs are built for massive parallel processing, and that generates a lot of energy, which, well, it manifests as heat.
And too much heat is bad.
Too much heat is bad.
Right.
When they overheat, their built-in safety systems kick in, they slow down to prevent damage. That's the throttling.
Okay, so the scenario we looked at had a few potential, maybe quick fixes, like limiting how much memory the GPU uses, or maybe shrinking the data set it's working on.
Yeah, options A and D in that question, basically.
Right. But the explanation points to actually improving the server's cooling system or the airflow as the real key to keeping things efficient. Why isn't just like shrinking the workload the best long-term answer?
Well, think about the bigger picture. While, sure, limiting memory or data set size might temporarily lower the heat.
It works for a bit.
It works for a bit, yeah. But you're also fundamentally limiting what your AI can learn or how fast it can learn it. It's like putting a governor on a powerful engine. You're capping its potential.
Ah,
Enhancing the cooling, though, that tackles the core issue directly. You improve airflow, maybe use better fans, or even go for advanced stuff like liquid cooling.
right.
You allow the GPUs to operate at their full potential without hitting those temperature walls.
So the core insight here, for me at least, is that even the most advanced AI is still limited by basic physics, like keeping the hardware from melting, basically.
Pretty much.
And inefficient cooling just directly chokes the GPU performance, which then caps your AI's potential. Is that a fair way to put it?
That's an excellent way to put it, yeah.
Yeah.
You want to enable the hardware, let it run optimally, not artificially hold it back.
Right. Okay, makes sense. Now, here's where it gets really interesting, I think. We hear so much about these huge language models.
Oh, yeah, LLA.
And our next concept
Yeah.
tackles how to actually make training them much, much faster, but without losing accuracy.
It's the dream, right?
That is the dream.
Yeah.
This gets us into computational optimization, which is critical. Training these enormous models takes just a tremendous amount of processing power and time. Weeks, months sometimes.
Sometimes, yeah. So any technique that can speed things up,
Yeah.
Without hurting the quality of the final model, that's incredibly valuable.
So the scenario we're looking at points to something called mixed precision training with tensor cores as the most effective way, not just like cutting down training time randomly or swapping hardware.
Right. Option B in that question.
Can you break down what mixed precision actually is and why are these tensor cores so important?
Absolutely. So traditionally, deep learning models did their math using 32-bit floating point numbers,
Okay.
FP32.
Okay. Standard stuff.
Standard stuff. High precision, but they're computationally heavy. They take up more memory. And mixed precision training is this clever idea where you use a combination, You use lower precision formats like 16-bit FP16
Yeah.
for most of the calculations.
Okay.
But you still use the full 32-bit where you really need that extra precision, maybe for stability, keeping things accurate overall.
So it's like a smart trade-off.
Exactly. It's a smart trade-off. You sacrifice maybe a tiny, tiny bit of numerical precision in some places for a massive leap in speed and memory efficiency.
And the tensor cores.
Ah, right. So NVIDIA Tensor Cores, they're specialized units built right into the GPU hardware. They are specifically designed and optimized to just crunch through these mixed precision calculations incredibly fast.
So they accelerate that specific kind of math.
Precisely. They lead to really significant speedups in training, use less memory, and usually without any major drop in the model's final accuracy. It's a huge win.
Okay, so basically we're telling the computers, do the easy math with smaller numbers to go faster, but use the harder, more precise math where it really counts.
That's a great analogy, yeah.
And these tensor cores are like dedicated express lanes on the GPU highway just for these types of calculations.
Exactly. They provide a huge acceleration for those specific mixed precision operations. It's a key piece of modern GPU architecture for AI.
Makes sense. Huge speed up potential. Okay, but what happens when you've got all this powerful hardware, the cooling's fine, maybe you're even using mixed precision, but it's still not being used to its full potential?
The utilization problem.
Yeah, question 3 presents the situation where GPU utilization in an AI pipeline is surprisingly low, like below 50%.
Yeah, and this is a frustratingly common issue in AI ops. You've invested all this money in these powerful processors, right? And they're just sitting idle waiting much of the time.
Like having race cars stuck in traffic.
Exactly. That's a perfect analogy. All that potential just wasted.
So the question suggests a few possible reasons. Maybe the GPUs are overheating after all, or maybe the AI model is too small for the hardware, or not enough power.
Right. Those are options A, B, and D.
Mhm.
Plausible, but often not the main culprit in this specific low utilization scenario.
But the explanation points to the data input pipeline as the most likely bottleneck. Why is the speed you feed data to the GPU so crucial for keeping utilization high?
Well, think of it this way. The GPU is incredibly fast, right? A processing beast. But it can only work on the data it actually has.
It needs fuel.
It needs fuel, exactly.
Mhm.
If the system that's supposed to be loading the data, maybe pre-processing it and sending it over to the GPU, if that part is slow, the GPU just ends up waiting, twiddling its thumbs, metaphorically.
Okay.
It's like that high-speed assembly line analogy again. The machines are super fast, but if the parts are delivered at a snail's pace, the machines sit idle.
So the GPU is starved for data.
Starved for data. So optimizing that data pipeline, maybe using techniques like preloading data before it's needed. It's called prefetching. Or processing data in parallel using faster storage that ensures the GPU gets a continuous stream of data to work on. That maximizes its utilization and boosts the overall performance of the whole AI pipeline.
So a slow data pipeline. It's like having that Formula One car, but it's stuck in first gear because it's not getting the fuel fast enough.
Precisely. All that power going to waste.
What are some concrete ways to speed up this fuel delivery? You mentioned prefetching.
Yeah, prefetching is a big one. Load the next batch of data while the GPU is still busy with the current one.
Yeah.
Parallel data loading is key too, using multiple CPU threads or processes to load data simultaneously.
Okay.
And of course, the storage itself matters. Using fast storage solutions like NVMe SSDs instead of older hard drives can make a huge difference in how quickly you can access the data in the first place.
Got it. So it's not just about having powerful processors. You need to make sure they're constantly fed with data. Keep them busy.
Keep them busy. That's the name of the game for utilization.
All right. Our next topic kind of shifts gears. Now we're talking about using multiple GPUs, but within a single server to really crank up training speeds.
Right. This is where we really start leveraging parallelism seriously. If one GPU is good, multiple should be better.
Right.
But you need a smart strategy for how to divide up the work.
Yeah, the question we looked at explored different ways. Like one idea was splitting the AI model itself across the GPUs. That's model parallelism.
Correct.
Or maybe just copying the entire data set to each GPU, which sounds inefficient.
It is, yeah. That's option B, generally not the way to go.
But the explanation highlights data parallelism using synchronized mini-batches as the most efficient method, especially for a single server setup. Option C. Can you walk us through how that works and why it's usually the best approach here.
Sure. So with data parallelism, the basic idea is you make a complete copy of your entire AI model on each GPU in the server.
Okay, identical copies.
Identical copies.
Yeah.
Then, instead of giving each GPU the whole training data set, you chop the data set up into smaller chunks called mini batches.
Right.
Each GPU gets a different mini batch to process independently and simultaneously. So they're all working on different pieces of the data at the same time.
Parallel processing.
Exactly. Now, after each GPU processes its mini batch and calculates how the model should be updated, these updates are called gradients.
Ah, the learning signals.
The learning signals. Yeah, good way to put it. After they calculate these gradients based on their own little piece of data,
Yeah.
they need to communicate. They synchronize,
To talk to each other.
talk to each other, essentially. They average or combine their calculated gradients across all the GPUs.
Why do they do that?
Well, this ensures that all the copies of the model learn consistently,
Yeah.
benefiting from the work done on all the mini batches, not just their own. It keeps the overall model training coherent.
Okay, so they learn together even though they work separately for a bit.
Precisely. And for a single server, the communication needed for this synchronization, it's usually pretty fast and manageable. The GPUs are close together. So data parallelism ends up being a very efficient way to use the combined power of multiple GPUs in that single box.
It's like having a team of students, maybe, all working on different sets of practice problems in
Yeah.
mini batches.
Yeah.
And then they get together, compare notes, average out their answers, and everyone updates their understanding based on the whole group's work.
That's a fantastic analogy. That's exactly the spirit of it. They work in parallel, then sync up to share the learning.
Cool. So that seems like a really effective way to harness parallel power within a single machine.
Now, let's zoom out, like way out.
Bigger picture.
Bigger picture. What are the really crucial things to think about when you're designing an entire data center for AI? Especially when you're planning for long-term scalability, needing to potentially add way more GPUs down the line, using NVIDIA GPUs specifically.
Right. Now we're moving beyond just one server and thinking about the whole ecosystem, the foundational architecture for an AI factory, essentially, that needs to grow.
So the question we looked at touched on things like, just cramming the maximum number of GPUs into each server, or the type of storage you use, like direct attached storage.
Yeah. Options A and B.
Huh.
Important considerations, maybe, but not the most critical for long-term scaling. Right. But the key factor, the really critical one identified for that long-term scalability was having high bandwidth, low latency interconnects. Option C again. Why are these connections, these pathways between components, so vital when you might end up with hundreds, maybe thousands of GPUs?
Because as you scale up, as you add more and more GPUs, both within servers and especially across different servers, the ability for these processors to talk to each other quickly and efficiently becomes absolutely paramount. It becomes the bottleneck if you don't get it right.
Oh, okay. Communication speed.
Communication speed and capacity. High bandwidth interconnects, think things like NVIDIA's NVLink inside a server connecting GPUs directly, or technologies like InfiniBand or high-speed Ethernet for connecting multiple servers together.
Gotcha.
These act like super-fast highways for data. They allow for the rapid transfer of huge amounts of data between all the GPUs. This is essential for distributed training, where you're sharing not just the initial data, but also all those intermediate results and those gradient updates we talked about. They need to fly across the network.
So if the connections are slow,
If the connections are slow, you create communication bottlenecks. The GPUs finish their work and then just sit there, waiting to send or receive data from other GPUs. It completely negates the benefit of adding more processors. You hit a scaling wall.
so it's like building a city with lots of powerful factories, but only having tiny country roads connecting them.
Exactly. You need the multi-lane superhighways.
Ugh.
The more GPUs, the more nodes you have, the more critical that high-speed, low-latency fabric becomes. It's the foundation for true scalability in large AI clusters.
We've talked about today, things like making AI even more scalable, or maybe more energy efficient, or even more accessible to more people.
Yeah, what's the next bottleneck? Or the next big accelerator?
Exactly. It's definitely a fascinating landscape to watch.